like this. All right, so let's get started today. This is the first hour of Physics 1C for September 27th, and the first thing I want to discuss is that we have an exam on Wednesday. And so the first exam is Wednesday. What is it going to be, the 29th, I think? Yeah, the 29th. It covers chapters 21, 22, and 23. That means that it covers electric fields, electric forces, Gauss's law. Please make it so that you're not... Alright, who is it? I'll just figure it out. Please don't have your mic on just open mic during class. You want to go on push to talk? Or just mute your mic, one of the two. Alright, so exam 1, Wednesday, September 29th, covers these chapters. That means it covers the topics of electric forces, electric fields, and charges, as well as Gauss's law, the concept of conductors in electrostatic equilibrium, and then what we're covering today, which is electric potential. Okay? Your homework for this chapter is due on Thursday. That does not mean it's not on the test, which means you should probably do this homework before Wednesday, really, before we have the exam. This concept of electric potential it can be pretty challenging, but it's not significantly different than what we've learned before, so it should be a little easier to get through since we're already familiar with a lot of the concepts. So we'll learn about it today. I highly recommend that you try to finish up that homework before the exam. Okay. That's the other reason I'm not going to move the due date, if that makes sense, Justin, for the question you asked earlier, is because, you really should finish the homework that's due on Thursday before the test. At least you should finish trying to solve the problems. And if you can't, then you're going to have a hard time on the test. I'm just going to remind you what you need to do. Is there a chance to have a crazy integral to integrate during the exam? Probably not, no. And if there's a difficult integral, I'll give you whatever information you need to help you solve it. I want to emphasize that in order to be prepared for this test, okay, as it may be a while since you took a test in person, you need to be able to solve all the homework problems, including the lab manual problems, from beginning to end without the help of someone, without the help of a book or a video or a tutor or a solution manual or your notes or your book or anything. I mean, you take the problem, a blank white piece of paper, and you can solve it from beginning to end. And that includes, if you really want to prepare for this test, that includes memorizing the formulas. Okay, I'll give you a formula sheet, but the formula sheet is utterly useless if you don't know what the formulas mean, which is often what will happen. So, if you really want to prepare for this test, you should memorize all the formulas and be able to solve every single problem that has been assigned this semester for the first 3 chapters from beginning to end on a blank sheet of paper with no other help. Is that clear? That that's the expectation? If you can do that, you will probably get an A or B on this exam. If you can do that for like half the problems, you can expect to get like a 50%. If you only know how to do a quarter of the problems, you can expect to get close to a 0% on the test. So I know that that's maybe difficult for you to do. I know that this will probably be the hardest exam we have in this class. It will probably be the hardest exam we have in this class. In order to keep things as to give you the best possible chance for success, I'm not going to put any multiple choice questions on this test. It's just going to be free response questions. There'll probably be 4 of them. Professor, would you say the mastering homework is similar to the test, or will it be closer to the lab manual homework? It's just going to be like all of it. And I think that the lab manual problems sometimes can be a little too challenging, so I won't put a lot of questions like that on there. But it doesn't mean there won't be questions like that on there. Probably there'll be questions that are similar to mastering physics. There'll probably be questions that are similar to the lab manual homework, and there may be some that are easier than the mastering physics too. It'll be a spectrum of problems, Miriam. It won't just be one type of problem, okay? And again, I don't want to disregard your question. It's a good question, okay? But I want to emphasize that you need to study all of the problems. If at this point there are homework problems that you still don't know how to do, today would be a good day to ask about them. Tomorrow during office hours would be a good time to ask about them. That's noon to 1 tomorrow. Other than that, we don't really meet again until we have the test. By the way, everyone shows up for the exam, okay? I'm going to have everybody split into 2 different rooms. Regardless of what your lab section is, everyone shows up for this, okay? Everyone shows up. Now, yeah, you should read all the homework. That's the best way to study, yes. Reading the textbook helps a lot too. Everyone has to show up. If you miss the exam and you don't tell me in advance why you're missing, and you don't have a really, really good reason, you're going to get a 0 for the exam. This is not an optional thing. This is not a, oh my god, I'm sick and I can't. You have to show up. Now, if you have symptoms of COVID, don't show up. But you need to contact me. If by the end of the test, if by 4:20 p.m. on Wednesday, I have not heard from you, I'm going to assume that you've basically decided that you're going to fail this exam. So you have to show up. You have to show up. Don't show up if you're sick, but it's not half the class. I just want to emphasize everyone has to show up for this, okay? Now, I have to emphasize one more time that this will 100% be the most difficult exam you take this semester for 2 reasons. One, the content is quite challenging for students of this level. 2, it's the first exam you're taking with me, so you're really not going to know what to expect. I mean, I'm telling you what to expect, but you won't really know until you take the exam. You know what I mean? So you really need to try to study for this exam. Now, I'm not suggesting you stay up all night long. It's extremely important, in fact, that you get a good night rest before the test. It will be challenging to you mentally in a way that requires that you have gotten rest. So if you've gotten through your college career and you've been coasting by and cramming for exams the night before and stuff like that, and you stay up all night long and you think that's going to help you to prepare for this test, it will not help you to prepare for this test. You're going to have your brain in a very lively state during the exam. That means you need to get some rest before the test. It doesn't mean you need to sleep all night long. It doesn't mean you need to get 8 hours of sleep, but you need to get at least 5 or 6 hours of sleep. You're young, you can get by on less. I would sleep as much as I can because the more sleep you get, the more alive your brain's going to be. You should also make sure that you focus on eating healthy before the test. That is to say, like, you don't want to take the test right after you've eaten like a bunch of pizza or cheeseburgers or something like that. You need to make sure that you kind of eat something that's reasonably healthy. You don't want like a lot of like fat being digested and grease being digested through your body while you're trying to take the test. It will definitely slow down your mental ability to function. Your body will kind of just go into a state of like just a funky state, right? So get a good night's rest. Study as hard as you can over the next couple days. Show up on office hours and ask whatever questions you have. After class today, if there are still homework problems that you don't understand to do, ask questions about them. And that's all that I'm going to say about the exam for today. Are there any other questions before we start with new things? I think I've answered all the questions in the chat. Be sure to email me if you can't make it for some reason, whether that be during the exam, before the exam, or whatever. Don't, like, I know that there are going to be some people that are going to try to not show up, and then they're going to try to get me to give them the exam on another day. I'm just going to tell you right now, unless you have an extremely good excuse, I'm not going to let you do that. And that's largely because in order for me to give you a retake on the exam, I have to sit with you for 3 hours while you do it. Okay? So if you're requesting that I give you a retake on the exam, okay, you better have a really good reason to make me have to work for another 3 hours when I have a pretty busy work schedule as it is. So if you want me to try to find an extra 3 hours in there that I can sit with you to take the exam, just understand that you're making a massive request, and it's not a good idea. Okay, so unless you're certain that you have COVID, you need to show up. If you feel sick at all, and you're coughing and all that kind of stuff, and you know for a fact that you're contagious, don't come. Like, don't risk that. Email me. That's a really strong reason. Like, if you wake up and you're sick, and you're really concerned about passing COVID along to a large group of people, that is a good reason to not show up. Okay. Avoiding extreme levels of being sick. Please, for God's sakes, show up on time. Don't make me spend another 3 hours in my week to sit there while you take an exam, okay? it is extremely selfish to do that for a reason that isn't, like, incredibly important. I hope that's understandable to you. All right, so let's get started with what we're going to talk about today. Today we're talking about electric potential, but the first thing we need to do is we have to talk about the concept of work. Now, in Physics 1A, you probably learned about work. You probably learned about two different definitions of work, right? There was one definition when you have a constant force, which is where you take work is equal to the dot product of force with displacement. Basically, force times displacement multiplied by the cosine of the angle between the two of them, cos theta. And the way you define this in your 1A class may have been like force times distance times cosine theta, or force times delta x times cosine theta, or something like that. But this is how work was defined. You have a force, you have a displacement, and you have some angle. Okay. To remind you how that's done, you could have, let's say, a flat surface here. I could have a box on that surface, and I could have a cord that's pulling in this direction with some force. And I could tell you that the object undergoes a displacement in this direction. So maybe the box moves from there over to here while you pull on it with this force. So you define this distance from here to here to be delta r. You define this angle to be theta and the force to be F. Then the work done on the object can be found by doing this right here. Another definition would be when you don't have a constant force, which is where you say the work then is equal to the integral of the force dot product with the displacement like this. This would be for a non-constant force. So constant force over here, and then non-constant force right here. So what we'd like to do is we'd like to apply this concept to the electric field, and we'd like to be able to figure out a way to talk about the work done by the electric field and how that's connected to the concept of potential energy. So in order to do that, the first thing we want to do is we want to set up an electric field that's uniform. So we're just going to draw some lines here to say we have a uniform electric field. That points from left to right. Let's use these 5 lines. We'll arrange them so that they're somewhat equidistant. All right, so uniform electric field pointing from left to right. Uniform means constant, and the same in all its parts. So we have a uniform electric field that we call E, with the size E. In fact, what we could do is we could say E is equal to some E sub x I hat or something like that. So uniform electric field that only points in the right direction, right? And what we'd like to do is to say, suppose that I take a positively charged particle right here, and I let the force on the particle, which we know that the force on this particle points this way. Call that the electric force. So we have an electric force on this particle and it points in that direction. And suppose that we want to figure out the work done as the particle moves from here to here. So we call this distance delta r. Draw another vector in here for that. And the particle moves from this location over to this location here, let's say. And let's say it has a charge that's equal to q. And let's say we want to calculate what is the work done by the electric field. I would say, well, the work done by the electric field, since it's a uniform electric field and the electric field is constant, is going to be equal to the size of the electric force dot product with our displacement vector. And let's say one other thing right here. Let's call this distance between these 2 points. Let's define that as being equal to d. Okay? So in a way, we could say that the distance d is basically the magnitude of the displacement. Like that. Okay, then we can say, here's something to review for the exam. What is the size of the electric force if I place a particle that has a charge of q into an electric field that has this size E? What's the size of the force on the particle going to be in terms of those variables? Yeah, Q multiplied by the size of the electric field, which in this case I'm saying is E sub x. So Q times the field gives us the force, right? Okay. So if I plug that into my equation right here, we're going to have Q times our electric fields, and then we have to multiply by the displacement here. And in this case, I'm going to say that's equal to D. And we also have to multiply by the cosine of the angle made between the force vector and the displacement vector. These two vectors are parallel to each other, which means the angle between the two of them is 0 degrees. So that means we've figured out that the size of this force, the work done, is going to be equal to Q multiplied by the electric field multiplied by D. That's the work done, right? Now, the goal of what we're going to do here is we're going to go from work into something called potential energy, which you've heard of before, and then introduce this new concept, which we're calling electric potential. So the next step is to take this and turn it into potential energy. And what I can tell you is that in order to do that, all we have to do is to use a relationship that, you may or may not have talked about this in your 1A class, I don't know. But in general, if I have a conservative force, the electric field is a conservative force field, I'll prove that here in a second, that the work done is always going to be equal to the negative of the change in potential energy. So U is potential energy, by the way. U is potential energy. That's the symbol for that. Does this look familiar to you all? Work done by a conservative force is equal to the negative of the change of potential energy. Can I mention the d cosine theta part right here? Well, look at this equation. You take force times displacement times the cosine of the angle between the two of them, Kavi. And the angle in this case is 0. You got it? Okay. It's the definition of the dot product. Then the other reason is because if the force was at some angle, we would only compare about the component of the force that would point in this direction. All right, so the work done by a conservative force is equal to the negative of the change of potential energy. In order to help you understand why this is even true, let's think about a really simple example. If I think of gravity, right, and I take an object, I don't know how well you can see that. Can you see this okay? Probably. If I take an object and I raise it from the bottom of my chin up to the top of my head. Okay, so I take this, I lift it from here up to here. What happens to the potential energy? Does it go up or down? Go from the bottom, and I pick it up and I lift it up to here. Has the potential energy, it's gone up, right? Okay. Potential energy gets higher and higher and higher the farther you get away from the surface of the Earth, right? Okay. So what about the work done by gravity? What's the work done by gravity as I lift this pen from the bottom of my chin to the top of my head? Is the work done by gravity positive, negative, or 0? Negative. It's negative, right? Because the force of gravity acts down. My displacement is up, which means the angle between those two is 180 degrees, which means the work done by gravity is negative. So let's think about that and see if it makes sense. You said delta U, which is the change of potential energy, is positive, but you said the work done by gravity is negative. And that's consistent with this equation right here, right? So what that means is if we want to think about what the change of potential energy in what we just described here is, the change in potential energy should be equal to the negative of the work, which is negative Q Ex times D. So in the particular setup that we have here, where you have a positively charged particle and it moves from here to here, what we're saying is that this particle has lost energy. It's lost potential energy. Does that make sense? Does that seem reasonable? I'll move my thing up. I see it's kind of blocking this out. So I'm saying that according to what I just wrote down here, we're saying the change of potential energy for my particle is a negative quantity. Does that make sense? The particle moved from here to here, And we're saying now it's at a lower potential energy. So what we would do is we'd say, suppose that we say this is its initial position, and this is its final position right here. In order for this to make sense, what we could say is that, let's say that we define its final potential energy to be 0, then its initial potential energy would have to be equal to Q times EX times D, because according to what this says, delta U, change in potential energy, is equal to the final potential energy minus the initial potential energy. Usually when we describe potential energies, we talk about reference points, so you can kind of always pick one to be 0. So plugging in these numbers, if I say U final is 0, and I say U initial is Q times EX times D, then we get that delta U is equal to negative Q EX D, right? Which is consistent with what we got over here, right? Now, let's see if this makes sense if we compare it to gravity, okay? Actually, let's do this part first. Let's see what would have happened if we moved at an angle. Let's do that. So let's take our same picture right here. And let's see what would have happened if we moved through an angle. So what we'll do is, let's redraw some of this stuff. Okay, let's say instead of doing it as we just did, let's say that our particle started here. So we have a positive Q right here, right? And let's say that I move it to here, okay? But I do so in such a way that the distance down here remains the same. So from here to here, the distance is still going to be d. Okay. The displacement of my particle is now going to be from here to here. Okay, this is going to be my displacement. We'll call that delta R. And I'm also going to label on here the direction of the force on the particle. So the force on the particle is going to point like this. Okay, that's my electric force. And I'm also going to throw in here an angle. We'll call this angle right here theta. And I guess that's all we need. That's all we need. So let's say the particle moves from this point to this point right here. Let's calculate its change in energy, okay? And let's do that in the same method as we did before. So we start off by saying the work done as the particle goes between these points. Maybe we label them. Maybe we say A and B or something like this. As the particle moves from point A to B, we want to find the work. We know that work is defined as we take the electric force and we dot product it with the displacement, which means we take the size of the electric force, which is Q multiplied by E sub x. We dot product it with our displacement vector, which I'm just going to call delta R, and I'm going to write magnitude around it, so the length of this displacement vector here. And then we have to multiply by the cosine of the angle theta between delta R and the force right here. Writing that all together, we end up getting Q, EX, and then delta R, magnitude cosine theta. But if you look on our picture right here, if I drop a line from here to here, right, and it makes a right angle like this, then in this triangle, delta R times the cosine of theta is equal to D. Right? So our answer for the work done is still the same as it was before. Which also means that the change of potential energy is the same as it was before. So when we compare these two answers, we compare this one with this one here, we get the same answer in both cases, right? It didn't matter what path we went along, okay? It seems that this point B and the point that we got to here seem to have the same electric potential energy. In fact, if we labeled this point right here as C, we could say that points B and C have the same electric potential energy. That is to say, it takes just as much work to move a particle Q along the line AB as it does to move the particle along the line from A to C. And these 2 points, B and C, effectively have the same energy. Does that all make sense, what I just said?
Professor, can I come in on voice for a question?
Uh-huh. Uh-huh. Yes, go, please.
Yeah, sorry. I get how you get the negative QED in the above explanation in blue, but in red here, where you're doing it in this example with the moving the particle through an angle, I don't understand where that negative comes from.
Same place when you go from
Just
work to...
that work is okay.
Yeah, same
Got
place.
it. I see it there. All right. Cool.
Now, I'm not really justified to use this expression unless both of these are true. So this is there's a little bit of circular logic going here, but you all already know this is true from Physics 1A. All I have to do is prove to you get the same, the work done is the same. So in this case, and let me scroll up just a little bit. In this case right here, we got the same amount of work done. And we could have gone along all kinds of different paths and still gotten the same answer. So that's proof that the electric field is a conservative field. A conservative field is one for which the work done does not depend on the endpoints. Okay? Jasmine, to answer your question, the reason why is because in moving between these points, the height isn't important for electricity, because height matters for gravity, it just doesn't for electricity, I guess is the simplest way to answer your question. So those 2 points may have different gravitational potential energies, but their electric potential energy is the same. It's important to understand, your question brings up a good point, electric potential energy is not the same thing as gravitational potential energy. It's not the same thing as, like, spring energy. Those are all different kinds of potential energy. Okay? Like, with kinetic energy, there's only one kind of kinetic energy, right? Just 1/2 mv squared. Well, that's not even true, right? Because you've also got rotational kinetic energy. Potential energy is a little different. With potential energy, you're going to have a potential energy for gravity, there's a potential energy for electricity, there's a potential energy for springs, and you got to keep them all separate from each other. They're all measured in joules, but they're different concepts. Okay, same work done by the electric field in moving from A to B as from A to C. And if we were to try to figure out the work done by the electric field to move from C to B, for example, what would you get? The answer would be 0. Yeah, the work would be 0, which means the change in energy is also 0. So along this line right here, along this line that's vertical and is always perpendicular to your field lines, the electric potential energy is the same. Hey, does that sound like something you did in the lab? In the lab, we had this situation, right, where all of your electric field lines, right, were perpendicular to some other line along which the electric potential energy was the same. Now, you didn't measure electric potential energy, you measured voltage, but that is electric potential, as we're going to learn here in a second. Okay, so just a couple of pictures to compare this, to kind of drive home the idea. So here's 2 different scenarios, okay? In one case, we have an electric field E. The other case, we have a gravitational field G, okay? Now, when we talk about gravitational fields, right, what we're looking at here is what happens as these objects move from point A down to point B, right? What happens to the gravitational potential energy of your system when you go from A to B? Does the gravitational potential energy go up or down? It's less than 0, right? It goes down, okay? So potential energy is decreased here, right? What about the work done by gravity? That's greater than 0, right? Because the force of gravity is down, the displacement is down, so the work is positive. If we compare the exact same scenario to the equation on the left, right? On the left-hand side, sorry, I'm getting some kind of spam call right here. All right. On the left-hand side, it's an electric field, but the same concept. If I were to ask you, what's the change of potential energy due to the electric fields, you'd say here, this is also decreasing, right? Because you're going in the same direction as the field line. So that tells us something about potential energy. If you go in the same direction as electric field lines, your electric potential energy is going to go down because you're kind of using up the field. If you go against the grain, you go against the field, your potential energy goes up. That's something that you should be really familiar with, right? Because if I take this remote here and I go and I lift it upwards, you know you're doing work against gravity, right? Lifting an object, you have to do work against gravity. So that means you're going to higher potential energies as you go against the field lines. And you're going to lower potential energies when you go with the field lines. So does this concept make sense? Before we make it more complex. Now, what would the change of potential energy be in this case over here? Let's actually directly compare these concepts, okay? So in this case, the work done by gravity would be positive m times g times d, right? Where d in the case is this distance right here. The change of potential energy would be negative mgd, right? Over here, delta u, E, is going to be QED, and it'll be negative. And the work done by the electric field will be a positive QED. Now, when you put them on the same page like this, do you see the similarities between the two? Let me make one of these a different color. Okay, turn that off. Let's make these ones red or something. Do you see the similarities? You've got QE, mg. They're both multiplied by d. Right? Mg is the force. You add the distance in there, you get the energy, right? mgy. In this case, it's QED, mgd. Do you see how they're the exact same idea? They'll have the same units, too. This is measured in joules. This is measured in joules. So you take a force times a distance and you get work, right? And then you define energy based on that. Now, you can't always define potential energy. You can only do this if you have a conservative field. But the electric field's conservative. Just to repeat why that's the case. If I move from point A to point B in a uniform electric field along a distance that we call s, it's going to take the same amount of work as it would have been the case to move from A to C. And the reason why is because by moving at an angle like this, you're not doing anything except for the direction that you move parallel to the field. It doesn't actually take work. Okay, this is the thing that's important here. It doesn't actually take work to move from here to here, to move up, or to move from here to here to move down. That's no work. I can't fit it in there. It takes no work to move perpendicular to the field lines. What about gravity? Does it take any work for me to take an object and move it in this direction, left and right? No. It doesn't take any work to move at a plane level. It only takes work if I go up or if I go down. And if I were to move in some type of like a curvy pattern, the work that I need to move in some type of curvy pattern only depends on the endpoints, the ending point and the beginning point, and the total elevation change between those two. That's the power of energy, right? It allows you to handle systems like roller coasters, right? If I have a roller coaster that has this really complicated shape and I put someone on the roller coaster, right? And I want to figure out, I need to make this a little higher if they're actually going to be able to go over the loop, but suppose they're moving, right? And I want to figure out, how high of a point can they reach right here? You know from your Physics 1A class that if you want to figure out how fast does this thing need to be going to actually go around this loop right here, you can just think about it in terms of energy. You don't need to worry about the fact that the path is really curvy like this and deal with the fact that the angle between the force and the weight, the force of weight and the track is changing all the time. And instead, you could just use energy because all you care about is, okay, if I start off at some elevation right here and I need to get to another elevation right here, all I care about is the initial height and the final height, right? That's all you care about. And that's the power of talking about energy, right? So we want to use that concept, and we want to come up with a way to talk about energy in electricity. But the thing we really want to do is we want to get rid of this Q. Because we often don't know what the value of the charge is. Or if we do, it's super tiny, like an electron charge. Or we're moving trillions of electrons between 2 points. In that case, we don't really want to deal with the charge. We want to eliminate the charge. We want to know what the energy per charge is, so that then if we know the rate at which charges are flowing, we can figure out the rate at which energy is flowing. So that's the next thing we're going to do. But before I do that, does anyone have any questions about these concepts? Okay, so let's define what's referred to as electric potential. You'll notice the word energy is not on here. It's just electric potential. I'm going to say this is the potential energy potential energy per unit charge. Okay, so we just said that we could define our delta U, right, as being equal to a negative Q times an electric field. I'm going to drop the subscript for this one, times D, right? All we're going to do is we're going to move the Q over to here, okay? We're going to say let delta V be equal to the change in potential energy divided by the charge. In our case, that would be equal to negative E times D. Okay, this is electric potential. So delta V stands for electric potential difference It requires 2 points. It's often measured in volts. The unit is volts, and we can say that 1 volt is equal to 1 joule per coulomb, a very important conversion factor that you may need to use from time to time, or you may need to remember from time to time to do like unit analysis. So delta V is electric potential difference, 3 words, with a unit of volts, and then we can define V to be just equal to the electric potential energy at a certain point divided by Q, and this is electric potential. This can be relative. Delta V will always be the same no matter how you define it, though. And that's really all electric potential is. We're just going to divide out the Q. And then we can talk about the potential difference between certain points. And I'm going to give you a really, really simple example of this to help you understand how it works. So suppose that I have an electric field. No, Justin, that's not right. No, it's not the same. It could be the same in a particular case, but in general, it's not the same. All right, so we're going to take a few electric field lines here. And we're going to use numbers and value and symbols to make this hopefully pretty simple for you. Okay, so suppose I have a region of space, right? And I tell you that in this region of space, the electric fields is equal to, let's say, 10 newtons per coulomb times I hat. Okay, so positive x direction points to the right, and we have 10 newtons per coulomb times I hat, right? And I want to define what the electric potential is at certain points along here. So we're going to come to points that are going to be equally distant from each other. So we'll pick a point here, pick a point here, here. Try to make these equally distant, hopefully, from each other. And, all right. Now, according to our definition here, delta V is equal to E times D, right? That's what it says, and we know what E is equal to, right? And let's give these things some points. So let's call this, let's say that we have, is it going to make sense if we go up in distance? I guess it'll be fine. So let's say this is 0 meters. Maybe it's better if I write it here. 0 meters, and this is just 1 meter. Every one of these is a meter. So 1 meter, 2 meters, 3 meters, 4 meters. 4s never look like 4s. 4 meters, and then 5 meters. Okay. All right, so if I pick 2 of my points, let's say we pick this point and we pick this point here, okay? Let's write down what the potential difference between those 2 points are. So delta V, as we go from 1 to 4, all right? Point 1 to point 4, should be equal to, well, it says right here, negative E, so negative 10, times the distance. How far is the distance? It looks like it's 3 meters, right? 1 to 4 would be 3 meters, right? So I end up getting, well, what is this? Newtons per coulomb times meters. What is that going to give me? Well, a Newton divided by a coulomb times a meter, right? Isn't that the same thing as a Newton times a meter over a coulomb? But what's a Newton times a meter? It's a joule, right? So this is the same thing as joules over coulombs. Joules over coulombs. So this will give me joules over coulombs, okay? But we can actually write it in a slightly different way. Since we know that a Newton per coulomb times a meter is equal to a joule per coulomb, and we know a joule per coulomb from up here is equal to a volt, right? Then I can say that a Newton over a coulomb is the same thing as a volt over a meter, right? And instead of saying that my electric field was 10 newtons per coulomb, an equivalent thing to do would be to say it's 10 volts per meter, right? And if we define it by using that unit, well, then it becomes just a little bit easier to look at how the math works out, I think. Because if we put volts over meters in here, it's pretty easy to see, much easier to see, that 10 volts per meter times meters gives you volts, right? So, between points 1 and 4, the potential difference is negative 30 volts, okay? It's negative 30 volts. What about the potential difference between points 1 and 2? That would be negative 10 volts per meter. Remember that this negative sign is coming from our definition, right? Negative 10 volts per meter times the difference between 1 and 2 would just be 1 meter. So we would get negative 10 volts. All right, going from 1 to 2. So let's pick a point and let's call it 0, okay? And maybe we choose the one where the 0 is. So let's also figure out what the potential difference is between 0 and 1. Can anyone tell me what it is before I calculate it? If I go from point 0 to point 1, what's the potential difference between those 2 points going to be equal to? Also negative 10, right? Hopefully you can work out. It's the exact same as 1 to 2. It's just, yeah, negative 10. Okay. So we've got all our numbers right here. And now what we want to do is we want to come back to our picture, and I want to actually label some absolute points, okay? So what's the best to start with? Let's say that I choose that this point right here, okay? I define this to be 100 volts, okay? So we're going to say let this point represent 100 volts, okay? And then we know as you go from 0 to 1, what happens to the voltage? Does it go down or up according to this? It goes down, right? So what should I write if I call this first one 100 volts, right? What should I write as my next one? 90, right? So this would be 90 volts. This would be then 80 volts. And you know what? We're going to drop 10 volts for every meter we move, right? So hopefully that makes sense. It's 10 volts. Every meter we move, we drop 10 volts. 60 volts, and this would be 50 volts, right? In fact, all along a line, if I draw a line straight down like this, basically all along that line, we have 90 volts. All along this line, we have 80 volts. All along this line, we have 70 volts, and so on and so forth. Now, the important thing to understand here is that these voltages that I've chosen are random. Meaning, I could have started from 157 volts right here. This was 157, the next one would have been 147, 137, and so on and so forth. You get the idea, decreasing by 10 volts for every meter that you move, right? But nonetheless, all along this line, this is 100 volts. All along this line, this is 90, 80, 70, 60, 50. And you'll notice that every one of those lines makes a right angle with the electric field lines, and we call these lines equipotentials because the electric potential all along them, equipotential. Oh my god, I can't spell. Equipotential. There we go. Equipotential lines. They are lines along which the electric potential is constant, all along there, all along there, all along there. And we can start to say some things. I mentioned this during the lab, but I'm going to mention it now. If I place a positively charged particle right here, it is going to tend to move in this direction. That is to say that positively charged particles will tend to move from high potential to low potential. I'll just say positive charges move from high to low. And vice versa, negative charges move from low to high. Because negative charges move in the opposite direction of electric fields, right? All right. Does anyone have any questions so far? Okay. What do we say next? So we've defined what the electric potential is. It's delta U over Q. That's potential difference. Electric potential is just U over Q. Pretty good place to take a break before we move on to the next part, unless I want to ask a question before we go on break. Let me look real quick. I do have this question here. I guess we can talk. Yeah, let's just take a break right now. It's a really good time to take a break. We defined all the concepts. We'll get into looking at applications when we come back. Any questions? Wait, it's going to be 2:15, right? $2.17. We'll do $2.17. Okay. Whoops.